Hello, Mark. Hello, everybody out there. Welcome to today's webinar about Western blotting and the troubles you can have with this method. First of all, I want to give you an overview about the Western blot procedure, and then I will show you possible problems can be revealed by the detection system. So what can go wrong and how can you solve the problems. And at the end, you will see the way how to get a good Western blot. So let's start with the Western blotting workflow. So you can see it's a quite complex method with different steps. So why do you perform a Western blotting analysis? So first of all, you want to confirm the presence of a target protein in a special cell lysate or tissue preparation, and you want to obtain semi-quantitative information. So if a certain target protein is regulated in a special way by special substances and these things. So seems we have technical problems. Okay, here we are. First of all, there's the sample preparations, and this is at the start of the Western blotting procedure a very important step because you prepare cell lysates. You use cells from cell culture or plant cells or animal tissues, and you during lysis it is important to stop protein degradation by proteases or dephosphorylation by phosphatases. So you have to use inhibitors to get an optimal sample for your Western blot analysis. So after this, you go further in sample preparation. This is now the step for the sample preparations for gel electrophoresis. So you have the native proteins and you start denaturing them by adding SDS. It's a sodium dodecyl sulfide, which is a detergent, and unfolds the protein and give it an overall negative charge so that it can be used in the SDS page. In the SDS page, you use, for example, a mini vertical gel, and this mini vertical gel contains polyacrylamide. So the polyacrylamide is formed by strands of acrylamide polymers, which are cross-linked by bisacrylamide. And this matrix works like a sieve, where the proteins are selected according to their size. So after or during the electrophoresis, you will see that the large proteins will be in the upper part of the gel, and the smaller proteins will migrate through the gel to the lower part, towards the anode. So if you have separated the proteins by electrophoresis, then you will transfer these proteins onto a plotting membrane by electroplotting, for example. This can be done by semi-dry or tank plotting. First of all, you have to prepare transfer stacking. So you have some layers of filter paper Then the gel, the membrane, and again filter paper. The filter paper is soaked with the plotting buffer. This could be either Taubin buffer for tank plotting or a special buffer system for semi-dry discontinuous plotting. After you have prepared this stack, you have to remove the air bubbles with a roller or test tube or similar things. Then you put the transfer sandwich into a transfer cassette and perform tank plotting, for example. So, and again, the proteins are plotted via the anode, so that the because of the SDS loading of the proteins. So here's the way the protein is transferred out of the gel onto the membrane, and as I already told you, due to the negative charge, the protein is plotted in direction of the anode. After this is done, the protein is located on the membrane, and after this you can stain the total protein on the membrane using phospho red. This is a total protein stain, and this staining is a control for complete transfer, and is also a good method to mark each lane where the samples are run. Okay, after this you destain the plot with water, and the next step is following. It's a plugging step to plug non-specific binding sites on the membrane, so that you will not have high background signal. So the plugging agent is on the membrane surface where no protein is plotted on. As plugging agent, you can use milk powder or BSA, or as alternative to milk powder or skim milk, you can also use casein. After this, the first antibody incubation is following. The primary antibody binds specifically on a target protein or so-called antigen. It recognizes the antigen, binds, and the primary antibody can be hosted by mouse, for example, and this is very important for the choose of the secondary antibody, because the secondary antibody incubation is necessary to get a label onto the primary antibody, which can then be detected by enzymatic reaction, for example, and the secondary antibody has to be specifically against the, for example, the mouse primary antibody. And with the help of the enzyme label on the secondary antibody, the subsequent detection can be performed. For ECL detection, it's the horseradish peroxidase label. So now we come to the important point of the complete procedure. It's the detection. So how does it work? You add luminol enhancer solution and the peroxide solution to the Western blot, where the secondary antibody is already linked to the primary antibody, and then due to the enzymatic reaction, light is emitted at 425 nanometer, which can be detected either by film or by digital camera. So these are the most common issues when you try to detect Western blot signals in using film and something went wrong. So you may have high background, non or unspecific bands, no bands, white bands, uneven bands, or patchy spots all over the film or the membrane. So high background. What are the causes for high background? First of all, high concentration of the secondary antibody. As you can see in this titration, the higher the dilution of the secondary antibody, the better the signal gets. But if the dilution is too high, background becomes again an issue, because you have to expose longer, and then the background becomes again higher. Another point for high background is the interaction with the plastic used to wrap the plot into before film exposure. So you have to check whether the plastic is compatible with your method, and have to change or have to select a special quality of plastic. Another point is insufficient clocking. So if clocking is not really well, the membrane, which binds very well protein, also binds the antibody, and so you will get background signal. The next point is insufficient washing. So if there are still antibody residues on the membrane, so this will also lead to disturbances during detection. So another point is incompatible clotting agent. So if you use non-fat milk, for example, in combination with the biotin streptavidin-avidin detection system, you will get background because the avidin, streptavidin, will react also with a fat milk molecules and bind there. And when you add the biotinylated horseradish peroxidase, this will also give any signals to you. So another point is the handling of the membrane. When handling the membrane, it is very important not to touch the membrane with a fingers. Always wear gloves and use forceps. Always keep the protein side up. Never let the membrane get dry. And yeah, that's the main facts for the membrane handling. So another point for high background is overexposure, as you can see here on this film. So the signals are so strong that you do not see separate bands, but it's quite going into one another, the signal. So this is not quite good. So you have to reduce the exposure time. Here's an example for different exposure times. Here you can see the signal intensities of a 3-minute exposure, where you can well divide the lower signal from the stronger signal. But if you increase exposure time, it is difficult to distinguish between both signals, and the background also becomes higher. Okay, so the overexposure is a main problem for the detection with the film directly on the membrane. So you will have the signals directly on the film. Another system for detection is a digital camera system, where the membrane has a certain distance to the real detection system, and then you will have a better signal-to-noise relation. And this is also shown here. The dynamic range of the film detection is not as broad as the dynamic range of the digital camera system. So the higher this dynamic range, so the dynamic range is the ratio between the largest and smallest value of light quantity. So if this is higher, it's better to detect both strong and weak signals than in the film system. It is too low to separate these different signals well. So in general, the digital camera system is a better system for this detection, but it is also an expensive system, so you have to decide what method will be good for your applications, and if it's worth to invest in a CCD system, or if films are enough for your analyzers. So another cause for high background are contaminated buffers. So due to the substances used in blotting, these buffers tend to be contaminated with bacteria or fungi or these things. So if you are in doubt, just use fresh buffers, because this will be more time-saving than to start a completely new Western blot, because your first try was not good enough. So the next issue is are the non- or unspecific bands. What is the cause of these things? So first, the secondary antibody may not be specific. So if you have a secondary antibody which binds also to a target or an epitope on a protein you do not want to detect, it's a so-called cross-reactivity, you will also get bands, but these bands are unspecific. Another issue is the specificity of the primary antibody. So when you use monoclonal antibodies, which just recognize one epitope, one special epitope, this is not really an issue. But if you use a polyclonal first antibody, this could become an issue, because polyclonal antibody is directed against several epitopes of the same target protein, and this can be also lead to cross-reactivity on epitopes of unspecific proteins. So further, unspecific bands can also be obtained by some aggregation or fragmentation of the target protein. So the target protein, for example, has a middle molecular weight of 80 kDa. So if it aggregates, the aggregate will form larger complexes, and you will have a higher molecular weight, which reacts with the first antibody, or if it is degraded, as I already mentioned for the sample preparation step, you will get smaller proteins or peptides which react with your antibody, and this will also lead to unspecific bands. Another point which leads to unspecificity is the STS interference. Because of the STS page, the proteins are still loaded with the SDS, and this can interact via electrostatic forces with the antibody molecules, and this will also lead to an unspecific antibody binding. So why are no bands or very, very weak signals on the plot? This can be the cause of inefficient transfer. So if the proteins are transferred onto the membrane, everything is okay. But if the transfer conditions are not quite good, so too long, or the voltage is too high, so the membranes will be plotted through the membrane into the filter paper. And so you will lose the protein or part of your protein, and it won't be visible on the Western blot membrane in detection. Another part for this is an inefficient transfer. So heating during the transfer will also influence the transfer efficiency, because the proteins are degraded and these things, so nothing will be optimal for this. So to get better transfer, you also need an appropriate membrane. So there are two typical types for this: the nitrocellulose and the PVDF membrane. Nitrocellulose shows low background and is very easy to block, but it is not physically strong. It's very fragile, and it is not recommended for small proteins. Whereas the PVDF membrane has a high protein binding capacity and it is physically strong, but it requires methanol for activation before use, and it's highly hydrophobic, which can be an issue during the plot processing, because you have to make sure that the PVDF membrane always is completely covered with a fluid of buffer or these things. So no bands. Another reason is that the antibodies may have lost reactivity. So antibodies are also sensitive against heating and freezing. The effect on the antibodies is the same. They are not very well soluble, and so you have insufficient detection. The plotting reagent, the non-fat milk, may mask your target protein or the proteins at all, and then binding of the antibody is blocked. Okay. Another point is the inhibition of the horseradish peroxidase, because the detection is an enzymatic reaction where the enzyme reacts with luminol and peroxide, and light is emitted. So if you have sodium azide in one of your incubation buffers. So if it is overnight blocking or overnight first antibody incubation, you have to make sure that the sodium acid is completely removed before detection starts, because this will inhibit the horseradish peroxidase, and you will see nothing on the plot. Also, the contamination of the stock solution can lead to absent bands, so you have to make sure that these solutions are neither exposed to sun or not contaminated by bacteria. And yeah, it's something that should not occur normally, which causes no bands, is that you use incorrect antibodies. So if you use primary antibody which is not directed against the epitope you are looking for, or if the first and secondary antibody are not the right pair, so the species specificity of the secondary antibody does not correspond to the source of the primary antibody. Another important point is the antigen-antibody binding and the affinity or the strength of this binding. So if the antibody binds not strong enough to the antigen, so the strength of the binding is given by a so-called binding constant, Kd. And if this is not strong enough, the primary antibody can easily be removed by the washing and the other incubation steps. So now the next problem is the white bands on the film. Where do they come from? So white bands come from an excessive signal that is generated through the detection. So this comes by too high signal intensity. So that the signal cannot be transferred into a real good blackening of the film. And the next is the next issue are the uneven bands. This can not only be a topic of the gel matrix, but also of the samples loaded on the gel. So if the gel matrix gets too much voltage during the electrophoresis, it heats up, and this will cause disturbances into the gel matrix and leads to uneven or disturbed bands. So you have to avoid this. Another effect which leads to uneven bands are concentration differences between the different samples. This could be either high salt or protein amount. So if you put a high salt or high protein sample directly beside a low salt or low protein content sample, you will get a broad lane where the concentration is high, and a smaller lane where the concentration is low. And these disturbances can be avoided by not loading these samples directly in neighbor lanes, but to leave one lane empty and fill this lane with sample buffer. So where do the patchy spots on the plots come from? So it could be the contamination of the equipment used. So there may be polyacrylamide fragments, very small fragments on the plotting membrane, which react with the antibodies and then lead to spotty signals. Or you may have trapped air bubbles. So as it is shown here, the air bubbles were created during preparing the plotting stack, for example. So you roll over this and remove the air bubbles, and that's it. So patchy spots also can be caused by unevenly hydrated membrane. So as I already mentioned, it is very important to make sure that once the membrane is wetted, it is always wet during the complete procedure. So if you have aggregations of the blocking agent during the blocking step, this will be removed during the washing and the incubation steps, and then you will have a part of the membrane where no blocking agent is present when the antibody incubation is performed. And then the antibody binds unspecifically on this so not blocked part of the membrane, and you will get also patchy spots. Patchy spots can also be a result of the interaction of the plotting membrane with the sample tray. So therefore, it is very important to make sure that the protein bound side of the membrane is always on the is on the upper part of the tray and not on the bottom of the tray. And furthermore, aggregates which occur during the washing or the incubation steps, which are usually done in the presence of lower concentrations of the blocking agent, may also form these aggregates and patchy spots, because not really good soft milk powder, for example, can be found on the membrane and then reacts with a detection system, and you will get spots on the membrane. Okay, so now this is the way to get a good Western blot. So it's not a general procedure how to get a good Western blot. You have to optimize it for your special application. So for this reason, it is very important when you use a commercially available primary antibody and secondary antibody to work after the recommendations of the producer, because they do a lot of testing to find the optimal range for their antibody concentrations. If you use so-called self-made monoclonal antibody, you have to do optimization to get the best conditions for your special Western blotting application. So that's what I have to say about the troubleshooting during Western blotting. So if you want further information about this topic, you can contact me by phone or by email.